Hello everybody. In this video, we are going to learn to draw better Lewis structures. If you remember from Honors Chem, so many times people would come up and ask their teacher, my Lewis structure looks a little bit different than yours, but I followed the steps and all my numbers work out. Which one is correct? And the teacher would respond with, both, it's complicated, either one would be okay. Well, in this lesson, you're finally going to understand why your teacher might have drawn one version versus the one that you drew, and which one would be considered better. We're going to be looking at things like resonance, formal charge, and a reminder about our VSEPR shapes. Resonance is what happens when there are multiple ways to draw your Lewis structures that are all valid, meaning all the atoms are connected to the right atoms, the bonds are between the right atoms, lone pairs are in the right places, you've used the right number of valence electrons, etc. But that there are slightly different arrangements of those bonds and those lone pairs. So for example, here is a structure called benzene, C6H6. Each of these corners here is a carbon. It's a simplified version of drawing Lewis structures that you'll learn in college chemistry. You can see here that both of these structures have 6 carbons and they both have 6 hydrogens. But if you look very carefully, you will notice that the double bonds are between slightly different atoms. Here we have a double bond, but on this version it's a single bond. This is a classic example of where students would come up and say, I drew the one on the left and you drew the one on the right. Are they correct? Yes, they're both correct. One of the things that demonstrates that resonance is occurring is looking at bond lengths. You would expect that your single bonds should be longer than your double bonds. However, for this structure, benzene, when they measure those bond lengths in real life, they find out that all the bonds are the same length. They're somewhere between a single bond and a double bond in length. They're an in-between. They're an average, which is strange. We don't have a 1.5 bond, right? We're drawing single bonds and double bonds. So what's happening? Well, in real life, it's pointing out that something's not quite as simple as a Lewis structure. There's a little bit more going on here. We see that these resonance bonds are shorter than our single bond, therefore stronger, but they're longer and weaker than a double bond. And here's the thing that's hard to understand. Neither of your resonance structures that you drew are accurate. They're not. Lewis structure is too simple. In real life, this structure here is in between the two drawings. And we know that because we can measure it in real life now. We have actual data that shows that this top drawing is wrong. The bottom one is wrong. It's in between. You can have a bunch of resonance structures. You could have resonance of ions. Here we have the carbonate ion. One resonance structure has a double bond here on the left. One has a double bond going up and down. One has a double bond here on the right. Over here, this is acetate ion. One resonance structure has a double bond on the top. One has it down here on the bottom. You notice we put square brackets. If there's a charge, you put the charge, and we put arrows, double-headed arrows, between all of the resonance structures. Sometimes you may see online, instead of drawing all 3 resonance structures, somebody might just draw this. with a dashed line. In my opinion, I like the dashed lines because to me, it's really showing that all of these bonds should be identical in real life. It's showing that it's intermediate. It's not a single bond and it's not a double bond. It's somewhere in between. However, on the AP exam, if they ask you to draw resonance structures and you draw those dotted lines like that, they will not give you points. They want to see that you very specifically understand that these three things up here are the resonance structures. These are the different valid ways to draw your Lewis structures. I wish there was some consideration for using the dashed lines because that's a lot of people do that in real life. But I need you to understand that you can't do that in this class. You have to draw all of the versions with your double-headed arrows. Now, the formal charge is an idea that can help us figure out which resonance structure is considered better. Sometimes you would have drawn one and your teacher drew one and you're, wondering why did your teacher pick one resonance versus the other. It's probably because your teacher was out of habit using formal charge and they happen to remember and they happen to know which resonance structure is better. Now you will be able to figure it out as well. So formal charge is a method of essentially pretending that all of the electrons are divided up evenly. If we were to split the electrons in the bond and give one electron to one atom and one to the other, regardless of their electronegativities, what charge would those atoms have if you divvied up those electrons and made them be separate atoms again? It's not a perfect theory. It doesn't work perfect in real life every time, but it's one step closer to a better structure than you had in honors chem. And that's what we're doing here. We're baby stepping our way to more and more, better and better chemistry. In college, you'll probably learn even more stuff that's even one step further than this, right? So, when we're trying to figure out which resonance structure is better, there's some things you have to keep in mind. We want to minimize the amount of formal charge. Lower charges are always better. We also want to have any negative formal charge on the more electronegative elements. Because in real life, the more electronegative elements would be hogging those electrons more. And so we want to try to demonstrate that through picking negative formal charges on electronegative elements. So here I have three resonance structures. They all have the atoms connected in the right order. They all have the right number of electrons drawn. We are trying to figure out, of these three, which is the better one. Which one is your teacher probably going to put on an answer key? So thinking about the first bullet here, we want to have the smallest formal charges. If you look at the left and the middle, we have zeros and ones. But on the right, we have a 2 over here. That's bigger. So that's not good. The one on the right's not so good. Now we're trying to decide between the left one and the middle one. I need to remember my electronegativity trend from the periodic table to figure out which is more electronegative, sulfur or nitrogen. And if you look and you remember, you will see that nitrogen is more electronegative. So this structure here is preferred. You can see here we've made the lowest size formal charges we can, and we've put the negative formal charge on the more electronegative element. So if your teacher was going to draw one of these on an answer key, they would have drawn this middle one. So how do we figure out what the formal charge is? When we're trying to calculate the formal charge, there's a way to remember this, kind of like a little equation. You think about how many electrons should that element have if it was normal, and you subtract how many electrons it would have after you've divvied up everything in the bond. So the should is coming from the number of valence electrons. For example, fluorine should have 7, right? It comes with 7. When you're figuring out how many it has, you count up how many lone pairs there are, and you're going to take half of any electrons inside the bonds. And the reason we take half of the bonded electrons is because we're splitting them between the two atoms. We're divvying them up. If you have a single bond, atom A would get 1 electron and B would get 1. If you had a double bond, A would get 2, B would get 2. If you had a triple bond, A would get 3 of them, B would get 3 of them. So what we're really doing here is we're trying to figure out what the charge on the atom would be if you split that molecule into individual atoms. We see how many electrons that atom should have based on the number of valence electrons, and we subtract how many it actually has once it's been divvied up. Remember, we want to have as close to 0 as possible. Any negative formal charge should be on our electronegative atoms. And then the last one is the one that people sometimes forget, and that is whatever your sum of formal charges is, if you add up all your formal charges, it needs to equal the charge on the structure you're drawing. If it's a +1 ion, like you're trying to draw ammonium, it needs to add up to a +1. If you're drawing carbonate and it's a -2 ion, it needs to add up to a -2. That's the one I see people forget about. Let's do some practice. One of those things that's easier to see than to explain. Let's look at some examples. I have SO4 2-. I have a sulfate ion. If you follow the steps from Honors Chem for how to draw your Lewis structures, you would probably draw a sulfur with 4 single bonded oxygens. But if you look online or you look at maybe a teacher's answer key, you may see some different resonance structures. You may see one with a double bond. And you go up and ask your teacher, why is there a double bond? It didn't need a double bond. Or maybe you see one with 2 double bonds, which seems really crazy. Why would it have 2 double bonds when you can draw them with singles? It's because there's different resonance structures. So let's go through and try to calculate all the formal charges and figure out which one would be better. So if I look at this oxygen here, oxygen normally would have 6 valence electrons, but it's participating in a bond. There's 2 electrons in this bond, so oxygen's going to get 1 of them. So I end up saying that oxygen has 7 if I were to split this molecule apart. Well, if it normally comes with 6, if it should have 6, but now it has 7, that's a -1 charge. Let's look at the sulfur. Sulfur normally comes with 6. It has 6 valence electrons. There's no lone pairs on here, right? So it has 4 bonds. It's going to get 1 electron from each of those bonds. So this sulfur, if this was split apart, would only have 4 electrons. If it should have 6, and it only has 4, that's a +2 charge. So if I have a +2, and I have all of these -1s, you can see it adds up to a -2, which is what we want. So let's go through that. We had 6 valence electrons that oxygen should have. There were 6 lone pairs, and it got 1 electron from this bond. The sulfur should have 6 valence electrons. There were no lone pairs. There were 4 bonds, 4 single bonds, so it got half of those electrons. So 6 minus 4 is +2. And we double check that it adds together to give us our total charge. Let's look at this one. Do you notice how 3 of the oxygens will have a -1 charge? Just like over here. But this one, something's different about this one. This has a double bond. So let's think about how the electrons would work here. Oxygen should have 6 valence electrons. There are 4 here from the lone pairs. 6 minus 4. And then there's a double bond. That's 4 electrons being shared, so oxygen gets 2 of them. So 6 minus 4 minus 2 ends up with a 0 formal charge. So 3 of my oxygens are a -1. This is a 0, and this is a +1. Now let's look at this one. Our single bonded oxygens will have a formal charge of -1. Our double bonded oxygens will each have a 0 formal charge. And this time, look at the sulfur. The sulfur should have 6, comes with 6 valence electrons. There's 1 electron here. There's 1 electron here. There's 2 that it's going to get from the double bond, and it's going to get 2 from this double bond. So that ends up being a formal charge of 0 again. So when I look at this structure on the left, even though technically you use the right number of electrons, technically everything has a full shell, this is not great. Look at all these formal charges. So many formal charges. This one has fewer, so it's better. But the reason your teacher drew 2 double bonds when you didn't think it needed 2 double bonds is because this has the least amount of formal charges. This is the preferred resonance structure. So this is probably the one your teacher would have drawn out of habit. Why don't you try this one? Why don't you pause the video and see if you can figure out what the formal charges would be on each of these atoms and which is the preferred Lewis structure, which is the preferred resonance structure. Pause it and give it a try. All right, let's start on the left. We have a single bonded oxygen. So it has 6 valence electrons normally, and I'm going to see 6 here, And there's a single bond, so oxygen gets one more. So 6 minus 6 minus 1 gives me a -1. Nitrogen comes with 5, should have 5, minus 1 here, 1 here, and 2 here. 5 minus 1 minus 1 minus 2 gives me a +1. I have a double bonded oxygen, should be 6, 6 minus 4 minus 2 gives me 0. For this one, I have a single bonded oxygen, which is a -1. Here, nitrogen should have 5. 5 minus 2 minus 1 minus 2 gets me 0. And here, we have 6 minus 2 minus 2 minus 1 more gets me a +1. That's not good, is it? We don't want a +1 formal charge on an oxygen. That's gross. Okay, now over here, this oxygen should have 6. 6 minus 2 minus 2 minus 1 minus 1 gets me 0. Nitrogen should have 5. 5 minus 2 minus 1 minus 2 gets me 0. This oxygen's double bonded, 2 lone pairs, should be 6. 6 minus 2 minus 2 minus 2 gets me 0. Which of those structures has the lowest formal charges? The one on the right. That is the preferred resonance structure. Now, Lewis structures are what we call localized electron model. Basically, any model where you pretend like the electrons belong to certain atoms and certain orbitals is called localized electron model. When you draw your Lewis structures and you're doing your formal charges, that's what we're doing. Resonance, though, shows us that these structures we are drawing are not perfect. Resonance shows us a weakness. There are other better models. There are things called delocalized electrons, where they don't really belong to one atom anymore, do they? We know that delocalized electrons exist, but you can't really draw a Lewis structure that shows that because a Lewis structure is too simple. Localized electron models are not perfect. They're good for most things we do, but they're not perfect. Understanding that's one of the reasons we learn about resonance is important. Just like in middle school you drew board diagrams, and then you learned that was too simple. Then you learn about Lewis structures, and you learn about different orbitals. Well, that's too simple. One last thing you have to take into account that you did in Honors Chem is VSEPR, because VSEPR is going to improve our Lewis structures a little bit. Resonance improved them a little bit. VSEPR improves them a little bit. Valence shell electron pair repulsion. Remember, everything comes down to repulsions and attractions. Here's another example. when we're drawing our Lewis structures, we really want to take into account that those electrons are trying to repel each other. They are trying to be as far apart as possible. They want the largest bond angles they can get. They want lots of elbow room. You have to be careful that you are not just looking at your atoms. You have to look at any lone pairs on the center atom as well. They are really going to distort the shapes because they need to take up space as well. When you're trying to think about your VSEPR structure, I've seen teachers try to come up with all sorts of rules, all sorts of, guidelines for this. Really what you're doing is you're drawing a Lewis structure and then you're trying to spread things out. That's what you're doing. And you use a chart and you memorize it. You're going to use your AX formulas. If you don't remember those, go back and watch the Honors Chem lectures, practice that. Look at your VSEPR chart. It will have the AX formulas. Remember, AX is showing you center atom, number of atoms attached, and number of lone pairs on that center atom. If you add up X plus E, you get that steric number. It's not that the steric number in and of itself is helpful. It's that it helps us find what row on our chart to look at. To be perfectly honest, that's why we learn about steric numbers. You've seen charts like this, right? Where we're looking at the number of items attached and what shape does that result in. I tried to take all of the different VSEPR charts that we had and all of the AX charts and all of the hybridization charts, everything we've had, and tried to make one big mushed together chart. I like this one because I only have to look at one chart to see it. It has the steric number, it has X and E, it tells me the generic electron geometry shape, it tells me the hybridization, I have my specific molecular geometry name, I have bond angles, there's even little pictures to show you how to remember and see it in 3D. Hopefully that chart is helpful for you. And yeah, you gotta memorize your names and you gotta know your bond angles. It's, not avoidable. We do need to be able to do that so that we can adequately talk about the structures we're looking at. So start memorizing it if you forgot. AX2 is when we have two atoms bonded to something with no lone pairs on the center. And these will spread themselves out as far apart as possible, lots of elbow room, nice linear structure. Now let's go and add a third atom. Uh-oh, now they can't be 180 degrees anymore. Now they have to spread themselves out even further. You can see it ends up 120. I've seen teachers use balloons to try to they tie balloons together to show you that they have to spread themselves out. I tried doing that in class one year and the balloons kept popping and I could never tie them. It was like a total nightmare. So there's a picture for you. Now, if one of these atoms was a lone pair instead, it wouldn't be AX3, it'd be AX2E, because one would be a lone pair. So the electron geometry is trigonal planar. This still looks trigonal planar, but if I were to just look at the atoms themselves, it looks bent. So the electron geometry is really just looking at how many items are attached. The molecular geometry is looking at the shape the atoms themselves take. If we weren't caring about the lone pairs as one of the items in the picture. Both of these have a steric number of 3, don't they? They have 3 items attached. Now let's go add a fourth item. We're going to stick one more on. Your Lewis structure might look like a cross, right? One on top, one on the bottom, but that implies that it's flat. It's not flat. If this was flat, you would have 90 degrees between everything. But in reality, if they kind of spread themselves out in this 3D shape, like a tetrahedral, they get a little bit more space. Oh goodness, I just noticed a typo at the top and fixed it. So it's 109.5 degrees, not 190. Okay, 109.5. So that's a little bit better than 90 degrees, isn't it? So if my ACTS formula has 4 atoms attached, it looks like that. Tetrahedral. If I replace one of those atoms with a lone pair, I get AX3E, and that lone pair is going to squish those bonds a little bit, isn't it? It's going to squish them down. Little bit extra repulsion there. You end up with slightly smaller bond angles. That's important to understand. Every time you add a lone pair instead of an atom, you get a little extra repulsion, and your bond angles get a little bit tighter. I love these little 3D ones that rotate. There's a PHET simulation, P-H-E-T, that you can do to see this as well. Now let's replace one more atom with a lone pair. Now it's going to be AX2E2. It's going to be even smaller than 107.5. It's going to be a little bit smaller. And it's the molecular geometry. If you look, well, we know that shape. What's that shape? It's bent. Just like water, right? 2 atoms and 2 lone pairs is bent. Now let's add on one more atom. Now there's 5 things attached, steric number of 5. What ends up happening is when this extra atom comes in, those atoms that were on the bottom kind of bend upwards. And if you look, you end up with this flat triangle in the middle, don't you? You end up essentially making a pyramid on the bottom and a pyramid on the top, which is why it's called Trigonal Bipyramidal, because you have 2 pyramids and the base of them is this flat triangle shape. If you replace one of them with a lone pair, you get AX4E, which we call seesaw. If you ever played on a playground with a seesaw, you could see why you kind of end up rocks back and forth like a little seesaw. If you replace another one to have 2 lone pairs, that is flat, isn't it? That's what we call T-shaped. There's not a ton that have these funny seesaw and T-shaped. Make sure you practice those as well. People tend to forget them because they don't come across as many examples. And if I replace one more, if all of these equatorials, meaning the ones in the middle on that flat triangle, if they're all lone pairs spread out as much as they can, you're only left with an atom on top, an atom in the middle, and an atom on the bottom, which ends up being linear, doesn't it? If I was just to look at the atoms, I would just see this linear shape. But if I were to look at the lone pairs, I would see it's more complicated than that. It's actually this trigonal bipyramidal or trigonal bipyramidal. You'll hear both. Now let's add one more. Now we have octahedral. Sometimes people struggle with this because they don't understand why is it called octahedral and, when there's only 6 things attached. And it has to do with the number of faces that the 3D shape would have. That's where they get the octahedral name for this shape. So a little bit tricky. When you have 6 items attached, 6 atoms, 4 of them will end up equatorial, and you have your 2 axial, top and bottom. It's very similar to trigonal bipyramidal, but instead of a triangle planar shape in the middle, we have this square shape. If I were to replace one of the atoms with a lone pair, I don't have these 2 triangles on top of each other with my atoms anymore, do I? I just have one. We call it square pyramidal. If I replace one more, I'm going to put another lone pair on the bottom instead of an atom. Now, can you see that the atoms that are left are all of the equatorials and they're all flat? We call that square planar. Nice and flat. Some people are much better at seeing 3D shapes in their head than others. I really struggle with that. I have always had a really hard time visualizing 3D shapes. So I love that PhET simulation. I just stare at the molecules over and over, just move them around. I love the little ones that spin. It really helps me. Do what you need to. Make sure you can see them in your head. Okay. Now, one thing, just a little reminder about why would certain things bond? Remember that combining certain elements together can help them satisfy their valence shells to be a more stable position, right? So, for example, fluorine doesn't like to be by itself. Remember, it comes diatomic. If you notice, they each have 7 valence electrons. They're missing this spot. They're missing one here, so when they bond and they share, they each end up feeling satisfied, right? Remember that our carbon, nitrogen, oxygen, and fluorine really want to satisfy that octet rule. They play by the rules very often. You may hear some people talk about what they call the honk rule. That means hydrogen likes to make 1 bond, oxygen likes to make 2, nitrogen likes to make 3, carbon likes to make 4. They don't have to, but they like to. Remember, these rules are not very good. It would be better if we called them suggestions. Remember, boron and beryllium are pretty small elements. They do not want to make, lots of bonds. They don't really want 8 electrons. They're very satisfied with fewer. They make what we call deficient octets. Beryllium is happy with 4, boron happy with 6. Some of our larger elements that have d orbitals like to make expanded octets. They can get much larger than normal. One thing that tends to happen is that people will try to draw things like sulfur and phosphorus with expanded octets always, and they don't always need to have an expanded octet. They can have 8 electrons, so just be careful about those things that tend to break the octet rule. Sometimes they do, sometimes they don't. For AP Chem, what seems to be the general pattern is that in reality, we should always take into account formal charges to figure out which is the best resonance structure. But they will typically take any valid structure that satisfies those octet rules, a normal Lewis structure like you drew in honors chem. unless they specifically mention taking into account formal charge, or they make a comment like, draw the preferred Lewis structure. If they're alluding to somehow taking into formal charge into account, you have to. But if I were you, I wouldn't waste a lot of time always trying to figure out formal charges. There should be some verbiage, some kind of hint to do your formal charge. And if you get good at formal charge, it can be fast. You can kind of realize, hey, a single bonded oxygen with 3 lone pairs is always going to have the same formal charge. A double bonded oxygen with 2 lone pairs is always going to have the same formal charge. So it's not that I'm asking you to flat out memorize formal charge patterns, but if you do enough of them, it will become kind of ingrained in you and you won't have to do your subtraction as formally. Make sure you can explain it though, right? If I want to understand your formal charge, you have to be able to explain how you got the number you got. Now, Lewis structures, right? Please, 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 I am literally begging you, do not just randomly throw dots on your paper. I've seen teachers teach it this way, where they say, just put dots down until it works. And I just cringe. The amount of guessing and the amount of mistakes just goes through the roof. It's a nightmare. There is a set of steps to take. I cover it in Honors Chem. My Honors Chem lecture videos are on my YouTube channel. I'm happy to help you with Lewis structures. If you need some extra support, come in and access. Happy to help you. A reminder, the rules for Lewis structures that will work every time. Count and sum your valence electrons. Place your atoms where they belong using all the suggestions you learned in Honors Chem. Bond everything with a single bond. Try the simplest way first. Give every atom a full shell. Recount how many you used. If you used the right number, you're all finished and you're done. If it's not right, you need to fix it. If you used too few, stick those extra lone pairs on the center atom. Just cram them in. Make it look ugly. Who cares, right? It's the best you can do. It's the best you can do. If you use too many electrons, that's when you fix it with double or triple bonds. That's what I teach you in Honors Chem. Remember the suggestions for where to place your atoms? Hydrogen's always on the outside, right? It's that dead end. It can only make one bond. Your least electronegative atom goes in the center. We really like symmetry when possible, but the thing you have to take into account now that you're in AP Chem that can really change things for you is formal charge. Remember, you want the lowest formal charge possible. It needs to add up to whatever the molecular ion charge is, and you need to try to get your negative formal charge on the more electronegative elements. And don't forget, if it asks for all resonance structures, draw all of them, no dashed lines. One small thing I just want to point out at the very end, because I've seen a lot of mistakes with this, is we are so used to drawing our Lewis structures with lines and not dots that sometimes they'll ask you how many electrons are being shared, and people will tell me the number of bonds. They won't tell me how many actual electrons are being shared. So in something like this with a double bond, there's 2 pairs of electrons being shared here. There's 2 bonds, but that means there's 4 electrons total being shared. And likewise, for a triple bond, there's 3 pairs of electrons. There's 3 bonds, but that means there's 6 electrons being shared. So I know that was a lot. We covered a lot of ways we can draw better Lewis structures. And I think you can see now why we don't go into all of this in Honors Chem. If you were trying to learn Lewis structures for the first time and VSEPR for the first time, and we threw in resonance, and we threw in formal charge, I think it would be way too much for Honors Chem. So you can see you've just gone a little bit further, and now you can draw way better Lewis structures. So I hope that was helpful, everybody. Bye.